In this video, we're going to take a look at a dynamic programming problem called knapsack problem. So basically, a person wants to carry some fruits in a knapsack to get maximum profits. So here are the weights and the profits of the fruits. So we have these items: apple, orange, banana, and melon. And these are the weights for those fruits. So you can see here, apple has a weight of 2, orange has a weight of 3, banana has a weight of 1, and melon has a weight of 4. And those are the profits for each and every single fruit. So apple has a profit or a value of 4, and orange has a value of 5, and so on. So the capacity of a knapsack or the bag is only 5. So we can only take a maximum of 5 weight that is equal to 5, right? So items that has a maximum profit and the capacity is maximum is 5. So let's try to put some different combinations here. So we have different combinations. So one is we can add apple and orange into the bag, and this will give us a profit of 9, but the capacity is going to be 5. And we also have banana. So banana and apple, they will give us a profit of 7 and their capacity of 3. So it's under 5, so it's good. And orange and banana in this case will give us a profit of 8 and their weight is 4. But if we have banana and melon, they will give us the maximum profit, which is 10, right? So in this case, their weight is still under or equal to the capacity. So in this case, the maximum profit will be banana and melon, right? So in this case, this shows that banana and melon is the best combination, as they give us the maximum profit and the total weight does not exceed the capacity. And one thing to solve this problem is that we cannot break the item down. So if we have orange that has a weight of 3, we cannot cut the orange in half or anything. So these values cannot be changed. So you can see here we can make a table, right? The maximum of our capacity is 5, and we have weights and the value for each and every single item, right? So apple has a weight of 2 and the value is 4. So in this case, how can we solve this problem? So one way we can do this, we can use a brute force approach, right? Basically, what we're going to do is we can draw a recursion tree. And for each and every single items that we have, right, for each and every single list of items, so apple, orange, banana, and melon, we have 2 steps. Either we take the current item or we skip the current item, right? So in this case, you can see here at the beginning, we have A, right? So A in this case is going to be apple. It doesn't matter which item we're dealing with, right? It doesn't matter which item. But in this case, if I want to get all the combination and traverse all the combination, for each and every single combination, I want to see if that combination exceeds the capacity. If it doesn't exceed the capacity, I want to see if this combination has the maximum profit. If it does have the maximum profit, we're going to update the current maximum profit that we've seen so far. And then at the end, we're going to traverse the entire combinations. We're gonna try with all the combinations that we can have for those 4 items, and then we're going to return the maximum profit. So you can see here at the start, we have the value. We have A, B, C, D. We select none. We haven't put anything in our bag yet, and the profit so far is 0. The weight is so far 0 because we haven't put anything yet. So now we have 2 decisions. We select the current item or we skip the current item. So in this case, if we were to select the current item, right, then we have A. You can see here we have A in our bag. The profit in this case is 1. The weight is 1. And then if I were to skip A, in this case, we have nothing in our bag. So we can take B or we don't take B. So we have 2 decisions still. So we're moving on to the next item, in this case B, right? So either we select B or we don't select B. And at the end, you can see we have one path where we don't select anything at all. And in this case, it doesn't really work, right? In this case, our capacity is 7 and we want to have the maximum value. So the maximum value here, you can see is 0. So this path is not the maximum, right? So in this case, we keep going. You can see we can either take D. In this case, if we take D, then you can see we have 16, right? And the weight is 5. So the profit is 16. And you can see that in each decision, we have a branch, we have a path. So in this case, we traverse the entire path, all the branches. And at the end, you can see we have the maximum profit. In this case, the maximum profit is 22. And we only have to take B and D, right? So take B and take D. And how do we get here? Basically, here you can see we skip A, we take B, right? And in this branch, right, in this path, we also have two separate paths. Either we take C or we don't take C, right? Once we skip C, we have two decisions still. Either we take D or we don't take D. So at the end, you can see that once we traverse, right, once we iterate each and every single elements that we have, or go through each and every single elements, and making those decisions, you can see at the end, we can be able to decide if this is the current maximum profit that did not exceed, in this case, the weight is 7, did not exceed the capacity, right? So this will give us a time complexity of n to the power of n, 2 to the power of n, which is basically exponential, right? So the space complexity in this case is going to be big O of n. So in this case, the reason why we have exponential here is because for each and every single node or each and every single recursion stack, right, we have two decisions. Either we take A or we don't take it. Either we take the current item or we don't take the current item. So that's why we have a exponential time complexity. So basically, let's take a look at how we can do this in code, right? So here you can see this is our brute force approach. And basically this is our class, right? Our class, our knapsack brute force class. And we're going to have a main method, right? A static method, which we have some test cases. So one of them is just the example that we're given. So is this example right here, right? The capacity is 7 and the profit should be, the maximum profit should be 22. Okay, so we're expecting 22 here. And you can see we also have another two separate cases, separate test cases, right? And then the output should be expected 120 and 390, okay? So basically we're creating this class, create an instance of this class, and then we call this solve knapsack method, which pass in the capacity that we have, and then we can be able to return the maximum profit, okay? So that's our goal. And basically you can see that this is what I did. Okay, so basically I have a function that takes the capacity, and in this function I have a helper function. We're going to do this recursively, and basically inside this helper function we have a index, right? Because we're traversing each and every single items that we have, right? So because for each path, we're basically traversing each and every single item, A, B, C, D, right? We're traversing each and every single item that we have. So in this case we have an index. If our current index is bigger than the size of the array, then we can just return the current profits that we got, right? But first, we want to make sure the capacity is actually under 0, is actually bigger than 0, right? If we exceed the capacity, then in this case, then we have to return 0 because we cannot find a maximum profit, right? So after we do this, you can see we basically have two decisions. Either we take the current item or we skip the current item. So if we take the current item, then we're going to increase the index by 1, right? Doesn't matter which way we go, we have to increase the item by 1 so that we have to make the decision for the next item in the array, right? So in this case, our capacity here is going to be, because we're taking this item, right? So our capacity will change. The capacity will be capacity minus the current item's weight. So that will give us a new capacity because we're taking the current item into the bag. So now our capacity should be decreasing, right? So if the capacity used to be 7 and the current item has a weight of 5, then now the capacity should be 2, right? And then for the current profits, it's because we're taking the current item, so we have to keep that in account. So in this case, the current profits plus the current item's profit will give us the new profits after taking this item into our bag. And if we don't take this item, then we don't have to change the capacity of recurrent profits at all. So at the end, in this case, for each and every single recursion stack, we have two decisions. And after they backtrack, they're coming back to the stack, then we want to make sure we get the maximum, right? In this case, the maximum profit, right? And if there is no path, like for example, if this, you can see those reds here, like their profit is 33, but weights are exceed the capacity, then we just have to return 0, just like here. So then in this case, it's going to be comparing 0 with the actual value, right? So 6 comparing with 0 pretty much. So in this, sorry, 17 comparing with 0 pretty much. So in this case, when we're coming back, we basically compare and take the maximum path, take the maximum profit path, right? So in this case, at the end, we're returning the maximum profit. So now let's try to run our code. Okay, so you can see here for the second test case, we're expecting 120. And for the third test case here, we're basically expecting 390, right? And here you can see we have 22 here, and we also have 122 here, 120 here, and 390. Okay, now let's take a look at a better way to solve this problem. So a better way to solve this problem in this case is going to be using a top-down approach. And basically what we're going to do here is we're trying to memoize. We're trying to cache the result. So if I have a capacity to 7 and we haven't taken any items yet, then we have two decisions. Either we take the next item, or either we take the current item, or we don't take the current item, right? And that will affect the capacity and as well as the profits. But basically we want to cache the profits in a cache array, or in using memoization to cache the data, the pre-computed data, right? So in this case, what we're going to do is we actually going to compute the capacity and the index, right? So in this case, you can see here when we have a capacity that's 4 and the current item is the third item, then they will get the same result as if we have a capacity of 4 and the current index is 3. Right? Because in this case, they have the same position. Their capacity 3, they have all the choices they can take, right? And in this case, they cannot take duplicate items, of course, but they can have the remaining choices because they're currently at index 3. They have, let's say they have 2 items left, right? So they only have those 2 items to choose from. So in this case, their result will be the same. So in this case, we can be able to memoize this using cache. So in this case, here I have a code called Knapsack top-down approach. And basically, what we're doing here is we're basically going to memoize this using a cache 2D array. And the reason why we're using a 2D array here is because we have a capacity as well as index. So what we can do is it doesn't matter either we put the capacity, right? We can have a 2D array table, right, 2D array table, and we can have the capacity as the columns, right? So we have 1, 2, or 0, 1, 2, 3, 4. So 4 columns, and in this case we have capacity of 7. So ... to 7, right? So the columns all the way to 7. Rows in this case is going to be the number of items that we have. In this case we have 4 items. So 0, 1, 2, 3, 4, right? So we're going to have 4 rows. So what we're going to do is that once we compute this result here, you can see we have it is the exact same function, the code, but what I added here is I added this part as well as this part. And basically, first we check to see if we basically compute this result, right? Once we backtrack coming back to the stack, and then we coming back to this item, the stack, and then we can be able to compare the maximum value. Once we take the maximum value, we can be able to save it in our cache. And then in this case, we can be able to return our cache. But if we meet the same situation again, where we have the same index and the same capacity, if this does not equal null, then we can just return the pre-computed result, right? So this will pretty much save us a lot of time. So the time complexity in this case is going to be big O of n times c, right? The reason why we have c here is because capacity, in this case, because we're using a 2D array, and the rows is c, right? So is equal to the capacity, and we have n number of rows. N is basically number of items that we have. In this case, if we were to use a bottom-up approach, basically we're going to use the same table that we created last time using the top-down approach, where we have a cache 2D array, and the columns is basically the capacity, right? From 0, if we have a 0 capacity, what's going to be the maximum value, right? And if we have a capacity of 7, what's going to be the maximum profit, right? Or the maximum value. And same thing here, the column or the rows are basically the number of items that we have, right? So in this case, we have 4 items. So in this case, for each and every single position, what are we trying to get in our cache to the array? For each and every single items in the cache array, what we're trying to save is the maximum profit, right? The maximum profit that we can have for the current capacity if we only take or skip this current item, right? If we skip or we take the current item, right? So let's start with this one. If I have 0 capacity, right, and I'm only have 1 item, then what's the maximum profit? In this case, 0, right? For 0 for all of them, because in this case we don't have rooms to take any of them. And if I have only 1 capacity, capacity for the bag is only 1, then can I be able to take this item? And what's the maximum profit look like? So in this case, I have 2 decisions. Either I skip this item or we take this item. So if I skip, then the profit is going to be 0, right? But if I take this current item, then in this case, we put this item in because it only has a weight of 1. So the maximum profit is going to be 1. And same thing here, if I have a capacity of 2, then what is it going to be? In this case, if I have a capacity of 2, I can either skip or take. Of course, we're going to take it because we have 2, if we have a weight of 2, and the current item's weight is 1. So in this case, we can take 1, and then the profit is going to be 1. And same thing for all of them, right? So then, what about the second row? For the second row is the same thing, right? If I want to take this current item, right? So if I were to take this current item, in this case, it's going to be the current capacity minus the current weight. But the thing is that you can see here, the capacity is 1, and we cannot take this item because it's exceed the capacity, right? So in this case, we can only skip this item. So if I skip this item, then what's the maximum profit? Because we already computed this result, you can see if I were to skip this item, 1 element up, in this case, is going to be the maximum profit for capacity 1 for this item. Because we didn't touch the capacity, right? We didn't take anything, so the capacity is still the same. But we're just moving on to the next option in this case. Because forget about this option, we move it on to the next option. Now, in this case, we only have 1 option, and we know that we computed this. We know that the maximum profit at this current position is 1. So in this case, we have 1 right here, right? And then what about this? It's actually the same thing. In this case, the profit is, the capacity is 2 and the weight is 2, right? So now we can be able to take this item in our knapsack. So in this case, we can have a profit of 6, or we skip this item. In this case, if we were to skip this item, it's the same thing, right? If we skip, we did not touch the capacity, so we still stay on 2. We're just moving on to the next item. In this case, the next item has a maximum profit of 1. So 1 or 6, which one is bigger? In this case, 6, right? And now what about this one? Same thing. If I have a capacity of 3, then in this case, we can take this item, of course, right? Because our knapsack has a capacity of 3 and the current weight is 2. So 3 minus 2, in this case, is 1. So in this case, if we take this item, the profit is 6. Plus, if we only have if we have 1 more capacity left, what's the maximum profit look like? Then in this case, it's going to be the previous row because we already took this item, right? And of course, because we're going this way, right? So in this case, we cannot go back anymore. There's only 1 option left. After we take this item, right? We done either skip or take this item. We done choosing those options, and we can only have this option left. So in this case, what we can do is we're going to go back to the previous row, right, which is this row right here, and then we're going to get the capacity minus the current capacity, which is going to be 1. 3 minus 2 is going to be 1. So 1 has a maximum profit of 1, right, for this item right here. So in this case, it's going to be 6 plus 1, which is 7. Okay, so 7, or we skip this item. Skip this item has a profit of 1, right? So which one has the maximum value? In this case, it's going to be 6 plus 1, right? So you can see here, this is our end result, where we have a 2D array filled with numbers, right? Filled with the maximum value for each and every single position, right? For each every single capacity and its current item or current index, we want to get the maximum profit. And we're going to start from here, right? We're going to start from the bottom, and we're going to work our way to the top right, So in this case, the bottom right is going to be the final endpoint. And basically, you can see here for each and every single position, for example, this one right here, we're applying this formula, right? For a current position, right? We want to get the maximum profit, right? So in this case, the maximum profit for this current position is either going to be if we take the current, if we skip the current item. In this case, if we skip, that's going to be the maximum profit for the previous item, right? The previous value is going to be 1. So it's either 1 if we skip, right, the maximum profit, or we take the current item's profit, which is going to be, in this case, 6, right? Plus, check to see if we can be able to get, in this case, it's going to be I, right? I minus 1, the previous row, at current capacity minus the current weight. In this case, the current weight is actually 2. So in this case, I cannot minus 2. In this case, this will give us a negative value, right? So we can only skip this item. So in this case, if we skip, then this is going to be 1, right? So if I take a look at another example, for example, 7, right? In this case, 7 has, for this position, the maximum profit, of course, is going to be 7. But in this case, the weight is 6, the profit is 6, the profit is 6, and the weight is 2. So if we skip this item, the maximum profit in this case is 1, right? If we skip, that's going to be the previous row at the same position. And if we take the current item, in this case, the profit will be 6 plus the capacity. In this case, the capacity is going to be cash. Capacity is going to be 3 minus the current weight, which is going to be 1, right? So we're going to get this one right here. So this one right here, the previous row at a capacity 1, which has a maximum profit of 1. So in this case, we have 1 here. So that will give us 7, and this will give us 1, and 1 is less than 7, so the maximum profit for this position is going to be 7, right? To do this in code, basically here you can see I have a class called Knapsack DP, and it takes the profits and weights, of course, just like usual. And in this case, I have just one method, right, which takes a capacity, and we're just going to basically we're just going to try to calculate the maximum profit, right? So I have a cache array, and by default it's going to be all zeros, right? And then we're going to start at 1 and we iterate to the end of cache at 0, right? We're basically just going to get the first row. We're basically just going to get the first row from here to here set to 1, okay? And then once we set this to 1, we're going to get the current capacity is equal to I, and then we're going to check to see if weights, the current weights, right? In this case, the current weight is this. We check to see if current weights is actually less than or equal to capacity. If it is, then we know the profit in this case is going to be here. It's going to be this one right here, right? So cache at 0 at I, the profits is going to be the current item's profit, right? And then in this case, we have a loop. Now this is our real stuff. We got this part done. We got this part done. And then we are starting from here. We're starting from the top left, and we're traversing to the bottom right. So in this case, we check to see if we have the skip maximum profit to be bigger, like whoever has the bigger maximum profit. Either we skip the current item or we take the current item, right? So skip, in this case, just like what I said here in the formula, is going to be cache at I minus 1 at a current capacity. And then J is going to be the capacity, I is going to be the number of row we're on. And in this case, we can we have to check to see if we can be able to get a positive value if we can take this item, right? After we take this item, can we get a positive value? If it is, then we can be able to take it, right? So I calculated take. In this case, take is equal to profits at I plus the next item's maximum profit, right? So in this case, we calculate the new capacity for the next item, right? Because we're going from bottom to top, so we can be able to have the next item, right? So in this case, capacity minus weights at I. So then we're going to assign that value to take. And at the end, we're just going to say cache at I at j is equal to the maximum value between take and skip. And then at the end, after the loop, we're just going to return the final element, right? In this case, the answer is going to be here, because for the capacity of 7 for this item, right, for this item right here, because we're starting from here, right, we're just like how we did in top down, we're starting from here and the capacity was 7, we're going all the way to here, right, we're going all the way to here. So in this case, for this item right here at a capacity of 7, the maximum profit that we can have is 22. Okay, so now you know how we can solve this problem. Let's take a look at how we can do this run this in code. And this will give us a 22, 120, and 390, right? So exact same as what we expected. And this approach will give us a time complexity of big O of n times c as well. And space complexity is also going to be big O of n times c. N is number of items that we have. In this case, we have 4 items. And c is going to be the capacity. In this case, this is the capacity that we have. And of course, we can optimize this. We don't have to use a 2D array. We can be able to cache the previous computer results, right? Because it seems like all we need to do here is be able to cache the previous computer results. In this case, we need this item, right? In this case, we need the previous row. In this case, all we need is the previous row. So we can be able to have just one array, which is going to be big O of c, right? In this case, we'll bring the time complexity down to a big O of c, because all we need is just the previous row, right? The previous row to compute the current row. And once we compute the current row, we can get the current row as the previous row, and the current row is set to a empty array or something like that. So this will give us a time complexity of big O of c, right? So this is how we solve this knapsack problem, and thank you for watching.